Hello, good afternoon, everybody. Welcome to the second lecture for Math 104. Hope you all are doing well. I am pretty happy. I got my new toy here. I have the tablet now, so hopefully this should run a little smoother. Um, so with that being said, why don't we just go ahead and jump into where we were before. So where we left off with the last lecture was we were discussing sets. So what we're planning to do today is we're going to finish up sets. We're going to discuss some real number properties, exponents, complex fractions, and hopefully finish up with absolute values and how to handle them. So let's go ahead and pick back up where we were with sets. So before with sets, we were already using U, which again we called union, right? And we were using union for kind of combining intervals when we were talking about the real number line. Well, as it turns out, we can use union for doing, things with sets as well. So as a quick refresher for you guys, what is a set? Again, a set is just something that contains elements, right? It's just going to be a collection of things, right? So we talked about natural numbers being the set of numbers going from 1, 2, 3, all the way to positive infinity. Integers being all of those, and 0 and all of the negative numbers all the way to negative infinity. And real numbers being the collection of all rational and irrational numbers, right? Real numbers are all the numbers that we commonly think of. Okay, so we can also just create our own sets. I can just say, okay, well, I have set A, right? And the way that we denote all of the elements inside of a set is we draw curly braces. So curly braces, curly bracket, and then we put in elements like, okay, well, A, B, C, so on and so forth, right? And what this is what this essentially says is that, okay, I have set A, which is the capital A, and in set A, I have the following elements, A, B, C, and then so on and so forth. There's, implies that there's more elements, right? So that's just the common convention for describing or building a set. So with union, there's also a separate function as well. There's a separate, piece of notation that we use, and that is kind of like an upside down U, and that's called intersection. So the way that we can kind of like differentiate between the two, obviously the one on the right looks like a big U, so you can think union, and then obviously then the one on the left means intersection. But what does it actually mean? What is it doing? So when we were talking about union, we were talking about all the elements from both sets, right? And I'll write union intersection. And hopefully you guys can still read my horrible handwriting. Okay, so when we were talking about union, we're talking about all of the things that were found, and it doesn't matter what set they're from. We just wanted to kind of push it together, right? When you think union, you might even think of the word marriage, right? And what's happening in marriage? Well, you have two different entities, and they come together, and the idea is for them to be one, hopefully happy, entity. Right? So you take two different groups and you make it one. And that's what we were doing on the real number line, right? We took two different pieces of the real number line when we had to use union, and we just kind of put it together. And we're saying, okay, well, we want this and we want this, so we made it one thing, right? Intersection is looking for elements found in, two sets where we're looking at the overlap of the elements. So think of a Venn diagram, right? So for an intersection, think of a Venn diagram. And in a Venn diagram, hopefully you guys are familiar with this kind of concept. In a Venn diagram, basically what you're doing is you're comparing two different things and you're looking for what's similar, right? So we're looking for this area here. We're looking for what is going to be the same in both, right? What is shared between the two? Whereas union, we're saying, okay, well, we have this entity, which we still care about, and we have this entity, which we still care about. So we're just going to say, okay, well, union, we're just going to put them together, and that'll just lead to an even bigger collection of things, right? So we're just putting two different things together in a union, making it a bigger thing. With an intersection, we're taking two different things and comparing them and picking a small group wherever things overlap. Okay, so hopefully that makes sense. Let me go ahead and clear this. And we will pick an example here. Okay, So let's assume that I have, and I'm going to keep that up for you guys. Let's assume that I have, whoa, what did I just do? Weird. A set A, and in set A we have elements A, B, C, and D. Right? Okay, say we also have another set B, and in set B we have C, D, and E. And lastly, we have a final set, which is set C. And in set C, there's only one single element, F. Right? And now, if you feel more comfortable with how you want to learn this, you can absolutely just go ahead and replace the variables with actual numbers. Just make sure that, wherever there are numbers found in both, that you use that same number, right? So there's a C and A, and I will underline it, right? So there's a C and A, there's a C and B. Just make sure that you use the same number in both if you wanted to, do that for your own notes. But for me, I'm just going to keep it general. We're just going to keep using variables here as elements and continue with that. Okay, so before we move on, the one last piece that we have to talk about is, okay, well, what if we try to take an intersection of things and there are no shared elements? There's nothing that is shared between the two sets. Well, we call that the null or the empty set. So an empty set or the null set is defined as, or the notation for it is kind of like a circle with a slash through it. Okay, please remember, I know that this might be a little confusing. When we were talking about sets, obviously I just told you want to use curly braces, and that's how you talk about all the elements in the set. This here though, if you do this, technically this means something different. It's not something that we're going to come across in this class, but in future math classes you might see it. Technically this means the set of the empty set, and this is incorrect. This is not what we're looking for, okay? So what we are looking for is if you have an intersection of two sets and you get no shared values, just draw the circle with a slash through it. Again, that means empty or null set, and that means that there's nothing shared between the two, okay? So again, just make sure you do not put curly brackets around the empty set. I just wanted to make that clear. Okay, so let's go ahead and given our three sets that we have here, why don't we find, I want to find A union B. I want to find A intersect B. And I want to find A intersect C. Okay, so let's start with number one, A union B. And what's going to happen here? And I'm just going to shrink this a little bit. Okay, so A union B. The idea here is we are taking all of the elements of the first set and just combining it with all of the elements of the second set. Now, a common misconception here is that you have to write the elements twice if they're shared. You do not, okay? So I'm happy I already have this underlined. We already have C underlined, but D is also shared between both sets, right? So we do not actually have to write these twice. A union B is going to be all the elements found in both, right? So that means that it's going to be A, B. We only have to write C and D once. So C, D, and finally E. And that's it. We're just taking two different sets, smushing them together, and now we have a larger set as a result. Okay? Hopefully that makes sense. All right, let's go ahead and move on to the next one. So now we're going to A intersect B. So with A intersect B, we now have to compare all of the elements from one set to another. Now, this is a really important note to make. You can only have at max, when you're talking about an intersection, you can only have at max in your new set that you're building the smallest amount from the set before. So what do I mean by that? Well, set B has three elements, right? It has C, D, and E. Set A has four elements, however, has A, B, C, and D. So what I mean by that is that even if all of the elements of B are going to be present in A, there's still going to be one element in A left over that wasn't in B, right? So we're talking about overlap, and that one element would be left out. So at absolute best, we can only have 3 elements in the intersection, which means, again, we can only go by the minimum amount. So that's a good way to like keep a mental note for yourself. You can like count the number of elements in the smallest set. And if you did an intersection and you end up with more elements than the number of elements in the smallest set, then you've done something wrong and you should go back and double check your work. Okay, so now let's go ahead and compare elements. So in set A, we have A and B. Do we see elements A and B in set B? No, right? Set B, we start at C. So that means that these guys, A and B, are going to be out, right? And I'm just going to undo what I just wrote over them. I just wanted to make it clear that A and B are not going to be present. Okay, so set C, or I'm sorry, element C is definitely present, right? We see that it's in both. So, okay, great. So C is one of the elements in the intersection. D is also shared between the two, right? So we have C and we have D. And E is only present in set B, and it's not present in set A. So that means it is not included. Hence, our intersection is only elements C and D. Okay? All right. And last but not least, we have A intersection with C. So A intersects C. And what's the idea here? Well, let's go back and look before we actually do anything. So we have A intersects C. With C, there's only one single element, right? F. Is F present in A, in set A? No. Which means that there's no overlapping elements. There's no elements that are found in both sets, so our intersection is empty. There's nothing that we can put in there. So what do? Well, no braces, right? Because again, we don't want to say the set of the empty set. We just say it's the empty set. It's the null set. And that's it. There is no answer. There's nothing that can be put here. There's no elements that is shared between the two. Okay? So at this point, why don't you guys go ahead and try your hand at problem number 1 in the classwork. Okay, so I'm just going to go ahead and clear this off, and you guys can go ahead and give number 1 a shot here. And in the meantime, when I clean this off, I will go ahead and start writing. Okay, so hopefully you guys have unpaused and given it a substantial effort as far as figuring this one out. So we are looking for, given set A has the following elements. It has -4, -2, 0, 2, and 4. Set B has the following elements. -3, 0, 1, 2, 3, and 4. So that 3 looked weird. Okay, and set C had also these elements: -4, -3, -2, -1, 0, and 2. And for whatever reason, my brain has a lot of trouble writing the right curly brace. Not sure why, but it's just the way it is. Okay, so what we have to do is we have to find A intersects C, B union C, and then a combination of kind of both, right? So let's try one at a time here. So A with the intersection of C. Okay, so again, what's the idea here? The idea is that we are just going to look for the elements that are shared between the two because it is an intersection, right? So we see -4 is found in both. So -4 is definitely in the intersection. -2 is going to be in both. -3 is not, however, right? -3 is only found in set C. So because it's only found in one of the sets, we do not include it in the intersection. 2 and 0. Well, should write them in order 0 and 2 just for clarity, but 0 and 2. And that's it. There's nothing else that's going to be in here, right? -3, -1, and 4 are all found in their individual sets, but not found in both. So intersection, we're only looking for the ones, shared between them, right? Okay, now let's look for B union with C. So B union C. And the idea here with the union is, again, we're just going to take all of the elements and kind of smush them together, right? We're taking two sets and making one larger set. And as a result, we just do not have to count the elements twice, right? So let's start with set C because that starts at a -4. So we know that -4 is going to be in here. -3 is it found in both, but we only have to write it once. So -3, -2, -1, 0, 1, 2, 3, 4, right? 2, 3, 4. Ran out of room, but that's okay. You guys get the gist of it. Right? So again, the idea is we just take two different sets, combine them into one larger thing when it's a union, and as a result, now we have this, right? Okay, I'm just going to clear this off here. Hopefully you guys got that. And the last one that we have to do is parentheses, A union with C intersected with B. So remember order of operations, right? Parentheses are always going to be done first. So what are we really doing? So essentially what we're going to do is we're going to break it into two different pieces. We're going to first do A union with C, and then after that, we're going to do the result of that intersected with B. Okay, so I'm going to use my red pen here, so that way we can kind of denote the A union with C. So what is A union with C? And we'll just do this off in a separate thing. So I'm just going to write an equal sign because, you know, this is what we're doing. So A union with C is we're looking for putting both of them together, so including all of the elements, right? So, well, -4, -3, -2, -1, 0, 2, and finally 4, right? Because 4 is in set A. Okay, and now the idea is we have this new set, and we are now going to intersect it with set B, which means we're going to take the elements that we have in this new set in red, and we're going to intersect it with set B, and set B found above is -3, 0, 1, 2, 3, and 4, right? So we're essentially just going to say, okay, well, what's found in both? Well, we have -3 in both, right? We have -3 here, and we have -3 here, okay? We have 0, and we have 0. We have 2, we have 2, and we have 4, and we have 4, right? So we have, other than -3, we have no other negative numbers. -4, -2, -1 all kind of just drop out, right? So our final result here is going to be -3, 0, 2, and 4. And that's it. That's all you had to do. So basically, it was just two different steps. You're just doing one first and then the other, and the order in which you do the steps is delineated by the parentheses. Okay? If you have any questions regarding this, try your hand at the homework first, and then please feel free to email me. Okay, let's go ahead and clean this up here, and we will move on. So that should do it for... hello? That should do it for sets. We will probably see a little bit of sets. I will probably quiz you guys on it, but sets aren't a huge part of this course. So if you really are struggling with it, just try your best, but it's not going to be the end-all be-all. Okay? What's more important is actually what's coming up right now. So what I want to discuss are real number properties, okay? So there are certain properties that hold for all real numbers. Now, I'm going to write these out, but I'm not going to give specific examples because I believe, hopefully, that you guys have seen these at least at some point during previous math classes, okay? If you need help understanding these, please come see me on the side, and then we'll talk about it in private, okay? So here are some of the properties that we know are true for real numbers and that we often use for real numbers. So the commutative property, okay? Commutative property basically just says, well, for addition, if we have A plus B that's going to be the same thing as b plus a. And the way that I remember that this is the commutative property and not any of the other properties is what's the operating word in, or the operative part in commutative? Well, it's commute, right? And what are you doing when you commute? You're moving. So basically all this says is that even if you move things around, even if you commute, like the variables, change places, it's still going to be the same thing, right? So again, this is basically just saying if you have 3 plus 4, this is going to be the same thing as 4 plus 3, right? Using particular numbers. Okay, so that's that for addition. There's also the commutative property for multiplication. We have a times b will always be the same thing as b times a. Okay, makes a decent amount of sense, right? Okay, so that was the commutative property. Now we have the associative property. So for addition, the associative property is a plus b plus c. Keep in mind, a plus b is currently in parentheses. And this is going to be the same thing as a plus, and now in parentheses, b plus c. So this is essentially just saying, and again, feel free to remember it this way. Also, actually, let me write down the multiplication associative rule. So this is a times b in parentheses times c is going to be the same thing as a, b, c. You can do it in either order. So associative, what is the operative word here, or the operative part? Well, it's associate, right? So it's who you associate with, who you talk to, right? So if we're talking about right here, we see that A and B are talking first, right? They're doing their thing, and then C is kind of like left on the outside, and that's the same thing as if B and C talk first and A will come in afterwards, right? So it's all about who the variables are associating with. Same thing, the same ideology for multiplication. Okay, so we've talked about commutative, we talked about associative, and for those of you who know the big three, you know what's coming, and that is distributive property. Okay, so distributive property, there's only one because it kind of encompasses both addition and multiplication at the same time. It says, okay, if you have some number times, in parentheses, b plus c, what you do is you distribute a to both values. So what you end up getting is whoa, that was bad. What you end up getting is AB plus AC. Now we can look at this with an actual example just to really hammer this down. I know I said I wasn't going to do many examples, but I just want to really make sure you guys understand this. So let's say, for example, we have 2 times 3 plus 4. Okay, well, obviously, what you can do is you can add the two numbers in the parentheses, right? And that would be 7, and then you get 2 times 7, which is 14. However, let's go ahead and use the distributive rule to like kind of hammer this down. So what we're doing is we're distributing 2 to both of these numbers, and we're keeping the sign the same, right? Because it's addition, we're going to keep it as addition. So this is going to be the same thing as 2 times 3 plus 2 times 4. 2 times 3 is 6. 2 times 4 is 8. And voila, we still end up with 14. So it's the same thing. 2 times 7 is going to be the same thing as 2 times 3 plus 2 times 4. And that's it. Distributive property. We get 14 nonetheless. Okay, so all you're doing is you're just taking your number and multiplying it against everything that is inside of the parentheses while keeping the signs the same. Okay, so those are the big three. There are a couple other properties that are still also worth discussing. So one of them is identity. So for addition, the identity property is anything added, whenever you add 0 to any number, you get that number back, right? And then for multiplication, our identity changes. It's no longer 0. Our identity is 1. So any number times 1 will also give you that number back. Now along with identity, there's also the inverse property. So inverse says, okay, well, for any real number, so if I pick any number, doesn't matter what it is, for addition, there's always going to be a negative counterpart to this number that will give me 0 when combined. So again, if we pick a particular number, right, say we're talking about 3, so with 3, there is obviously negative 3. and when we add them together, we get 0, right? Okay. It's going to be slightly different for multiplication. For multiplication, what it says is, okay, well, if we have any number and we're talking about multiplication, there always exists 1 over that number to where when we multiply them, we get 1. Okay. This also implies that a is not equal to 0, because if a is 0, then we get a 1 over 0 situation, and then the whole fraction blows up, and so does your calculators, and the world ends, right? And we don't want that to happen. So right here, again, as long as a is not equal to 0, you can pick any real number, a, and there will always be a 1 over that number, such that when we multiply them, we get 1 back. Okay. Also, if you guys have never seen this before, like multiplying like a real number against a fraction, all you're doing is you take this number and you multiply it against the numerator of the fraction, right? Because, and we're going to actually go over more detail fractions in just a second here, but if we have a times 1 over a, this is a is really just the same thing as a over 1, right? And when we multiply fractions, we multiply across. So in the numerator, we have a times 1, which is a. In the denominator, we have 1 times a, which is still a. And then that's 1. Okay. Okay. And then the last couple properties aren't technically, I mean, they are properties, but they don't necessarily have a name. They're just things that you guys should know. So if you have any negative number, so negative a, this is really the same thing as -1 times a positive number of a, right? So if you have -3, that's really the same thing as -1 times +3. Okay, and we already talked about this, but I am just including it in this lecture as well. When you have 2 negatives in front of any number, it will always return back the positive number, right? Because negatives cancel in pairs. Okay. So with that being said, let's go over a brief, very brief, hopefully. Let's go over a brief. We're going to go over fractions here and just make sure that everybody is on the same page regarding how to handle fractions, whether it's just general operations or even complex fractions. One of which was on your prelim exam, right? So let's say we're just going to pick real numbers here. Let's say we have 2/3 minus 1/2. Okay, so 2/3 minus 1/2. What am I doing here? What is actually going to happen? How do I possibly handle this? Well, we should know that when addition or subtraction of fractions are involved, what we have to do first is we have to get common denominators. Common denominators, and again, denominator is going to be this part, right? The lower number. So to get a common denominator, what that means is we have to somehow manipulate both fractions, or possibly only one fraction, but in this case, both fractions, such that the denominators change. And remember, guys, when we change the denominators, we also have to change the numerators. So before we even try to solve this, what I want to do is I want to explain that piece. Why do we also have to change the numerators? So if we come over here and we're just considering 1/2, right? And say I wanted to change my denominator to a 6. So what would we do? Well, we multiply the bottom by 3, right? And we say, okay, well, we get 6. But are we done here? Well, no, right? Because right now we haven't done anything to the numerator. And if we just left it as is, we obviously know that 1/2 is not the same thing as 1/6, right? So when we manipulate the denominator, we also have to manipulate the numerator and vice versa, because our goal here is to change how the fraction looks, but not change its total value. So instead of just multiplying the denominator by 3, we're also going to multiply the numerator by 3 as well, right? And remember, when we multiply fractions, we multiply across. So 1 times 3 is the same thing as 3 up top. 2 times 3 is 6. And now, hopefully, you guys should be able to recognize that we can simplify that fraction down if we needed to. 3/6 really is just the same thing as 1/2. And why does this make sense? Well, all we're doing is we're secretly just multiplying by 1, right? 3 over 3 is just 1. We're just cleverly doing it so that way we change the appearance of the fraction without changing the value. And remember, whenever we multiply any number by 1, we don't change the value, right? Any number multiplied by 1 just gives you gives you that number back. Okay. Ooh, oops. Okay. So with that being said, let's go ahead and find common denominators for this problem here. So obviously we have 2/3 minus 1/2. I think most of you guys can very obviously tell the common denominator here is going to be 6. So what do we have to do? Well, we have to change 2/3 to be something over 6. So 2/3, what we're going to do is we are going to multiply both the top and the bottom by 2, right? So we're multiplying by 2 over 2. And now, again, we still want this to be in terms of 6. So for the 1/2, we're multiplying by 3 over 3. And now what we end up getting is, remember, we multiply across. So 2 times 2 in the numerator, we get 4. 2 times 3 gives me 6. So 4/6. And again, that should make sense. 4/6 is the same thing as 2/3 minus 3/6, right? We just did that before. And now what do? Well, when we have fractions that are being subtracted or added, and they now have a common denominator, we can just combine them. So we keep the sign the same, we combine the numerators, and we keep the denominator exactly the way it is. So the denominator was a 6, we keep it as a 6. And now we just have 4 minus 3 up top, which is the same thing as 1/6. And we're done. That's it. Okay, so hopefully that isn't too hard for you guys. Hopefully that's a good refresher as far as how to do, addition or subtraction. Multiplication is going to be, again, you just multiply right across. So if we have A over B times C over D, we multiply across, right, and we get AC over BD. And that's it. And of course, feel free to substitute these with real numbers if it helps you conceptualize it better. But you just multiply across, and that's it. Now, one that you guys may have forgotten is division. So how do we handle division of fractions? Well, let's, again, have A over B, this time divided by C over D. Okay, well, what is this going to do? You guys may or may not remember keep, change, flip. What is keep, change, flip? Keep, change, flip is, well, we're going to keep the first fraction the same. We're going to change the divisor to a multiplication, and we are going to flip this fraction so that the numerator becomes the denominator and the denominator becomes the numerator. So what is this all going to look like when we do all the pieces together? Again, we're keeping the first fraction the same, so it's A over B. We're changing division to multiplication, so times, and we flip, so instead of C over D, it is now D over C. And we can now just multiply right across, right? So now it's A times D over B times C. And hopefully that makes sense. Again, keep, change, flip is something that I hope you guys have seen before. You don't necessarily need to do it this way. There's the longer approach, which may make more sense to you, and I have no problem going over that with you in private if you so choose. But I think that keep, change, flip is kind of intuitive as long as you can remember, KCF, right? So as far as complex fractions go, well, complex fractions, really all they are, A over B over C over D. Well, this is exactly what we had before, right? A over B divided by C over D. And we know that by keep, change, flip, this is going to just be the same exact thing, right? We're going to end up with AD over BC. And the reason is, again, this middle piece here, which I'll draw an arrow, that middle divisor, we know, again, a fraction implies division, right? So we're dividing two fractions. We're dividing A over B by C over D, and that's going to be this piece here, A over B divided by C over D. So all it is just breaking that complex fraction up into the two pieces, and then applying keep, change, flip. and that's about it, right? Things get a little more difficult when you have multiple fractions in the numerator, or multiple pieces in the numerator, or multiple pieces in the denominator. So what I want you guys to do is, using everything that we just talked about as far as finding finding common denominators and applying keep, change, flip, I want you guys to try your hand at the exact same problem that was on the preliminary exam, which I will include in your classwork here. So what that's going to look like is, on your preliminary exam, we had 2/3 minus 1/4, and this is all going to be over 3/4. Okay. So feel free to pause the video here, give your try at it, give yourself a couple seconds, and unpause when you're ready. Okay, so hopefully you guys gave it a good shot here and that it made sense. So what's our first step? Okay, well, our first step is we realize that, well, as far as denominators are concerned, we have a 4, and a 3. So 2 of them match, but 1 of them doesn't, right? So we still have to go through the process of making sure that our denominators are going to match. So let's go ahead and do that, and we have to do that at the very least for the top at first. Alternatively, there is another method, which I'll get back to you in a second. Let's just try doing this first, okay? So again, we're trying to find common denominators here. And what is our common denominator for this specific piece? Well, 3 and 4, the common denominator is going to be 12, right? So what we're going to do is we are going to multiply both the top and bottom of every fraction such that the denominator will equal 12, right? So for 2/3, we need to multiply by 4/4. For 1/4, we need to do 3/3. And for 3/4, again, 3/3. That's a 3, I swear. Okay. Okay, so when we do that, we end up with, okay, now we have 8/12, right? 4 times 2 is 8, 4 times 3 is 12, and we arrived with 12 on the bottom, which is what we wanted, minus 3/12, and this is all over 9/12, right? Okay, so what can we do? Well, we can combine that numerator, the 2 fractions in the numerator, and I'm not going to write it all out because I think you guys can do that one yourselves. But what happens? Well, the denominator stays the same at 12, and then it just becomes 8 minus 3 at the top, right? So we just get 5/12 all over 9/12. Okay, so what do we do here? Well, at this point, what you can do is, again, you can do one of 2 things, and this is the alternative thing that I was talking about. It just really depends on the order at which you apply yourself. But if you want to go through with the same process that we were talking about before as far as keep, change, flip, well, sure, we can do that. Well, this is 5/12 divided by 9/12, right? Because again, that big long divisor symbol is just a divisor symbol. That's all it is. And now we're going to apply keep, change, flip. So we keep the first fraction, 5/12. We change this to be a multiplication. And now this is 12/9. And hopefully you guys remember that if you have something in both the numerator and the denominator, as far as multiplication is concerned, we can cancel them out, right? So we have 12 here, and we have 12 here, which is the same thing as 12/12, because again, everything is being multiplied. So because it's 12/12, it just basically cancels out to be 1, and we are left with 5/9, or 5/9. And that's it. Also, I just want to take a second here for the entire remainder of this class. Whenever we have a fraction, leave it as a fraction. Leave it as 5/9. I know that technically this is 0.5 repeating. Don't do it. Don't write the decimal. There's really no point. For one of the other things that was on the preliminary exam, there was a question that ended up being the answer was 1/25. You don't need to write 0.04. You can just leave it as 1/25, and that's absolutely acceptable and totally the correct answer. Okay. So with that being said, we have 5/9 here, right? Now, alternatively, what we could have done, and now I'm going to kind of write the same question again, just actually, you know what, we're just going to erase everything. Sorry. With the tablet, it lags if I write way too much without erasing, so I want to make sure that things don't end up lagging and ruining the video. Okay, so Let's go ahead and get rid of the green. So the alternative method here is we could have recognized that, okay, well, we have a a complex fraction here. What I want to do is I want to attack this by clearing the denominator of the lower fraction. So the denominator of the lower fraction I'm circling here. I want to get rid of this because if I can get rid of this, that'll make my life a little bit easier. That's one less fraction that I have to deal with, right? So what do I mean by get rid of it? Well, I mean that I want to multiply by 4, right? Because if I can multiply this fraction entirely by 4, then the 4 over 4 is going to cancel, and I'm just left with a 3, right? So we're going to do that. We're going to multiply this fraction by 4. But remember, whatever we do to the bottom piece of this divisor, which I just circled here, whatever we do to the bottom piece, we also have to do to the top piece. So now we're also going to multiply by 4. And I distinctly remember 2 of you guys tried this and 2 of you guys made the exact same mistake on this. So I really want to make sure that you understand what we're doing here is we apply 4 times 3/4, right? And this part's easy. 4 times 3/4, we just get, well, the 4 is going to cancel out with there, and we're left with 3 in the bottom. That's great. And now you've simplified things. You've made it a lot easier on yourself. The problem that, and the same mistake that both of you made, was this. You did not apply the distributive property. You needed to multiply 4 times both pieces of it, not just 4 times 2/3 or 4 times 1/4. Okay, so remember the distributive property, you have to take your number and multiply it by both pieces that are in the numerator, right? So now what we end up getting is we get 4 times 2/3, and that just means that you multiply the 4 times the numerator, which means we get 8/3. And 4 times 1/4, well, that's just 1, right? Because we get a 4 over 4 situation. So we get 8/3 minus 1 over 3. And, well, 1 isn't a fraction. I mean, it technically is, right? Because 1 over 1 is the same thing as 1. And I just want to make it in terms of 3 because we have 8/3. So we have 8 minus, ooh, sorry about that. Zoomed out very far. We have 8/3 minus 3 over 3, right? Any number over itself is equal to 1, and I just wanted to make my 1 in terms of 3. And we get 3 here. And now, what's the game plan? Well, 8/3 minus 3/3 is the same thing as 5/3. And this is all over 3, right? Okay, so 5/3 divided by 3, and we can go ahead and apply the same KCF model that we were doing before. So 5/3 divided by 3, and remember, for this to work properly, it has to be a fraction, right? So 3 is the same thing as 3 over 1. And now we keep change flip, and this is going to be the same thing as, and sorry, I'm just going to continue it lower so I have room. 5/3 KCF, we keep the 5/3 the same, change to a multiplication, and now it's 1/3. And 5 times 1 is 5, 3 times 3 is 9. We arrive at the same conclusion that it's 5/9. Okay, so you could have attacked this 2 entirely different ways. Complex fractions kind of give you the benefit of doing that, where if you want to try to clear denominators first, you can do that like we just did here. Or if you want to try to combine fractions or combine things in either the numerator or the denominator, that's also a totally acceptable way of doing it. Okay, and I do just want to make a quick note here, and I'm going to write it in red just so everybody's aware. Whenever you have a situation which is A over B divided by C, it's always going to be A over B times C. And what do we see here? Well, we have 5 over 3 divided by 3, right? So what it really comes out to be is 5 over 3 times 3, which is 5 over 9. Okay, so just a little trick for you guys to remember. If you have a fraction over like divided by an integer, it's just going to be that integer, multiplied against the denominator. Okay, so that is complex fractions in a nutshell. That was also a brief review of regular fractions, and hopefully that proved to be lucrative for you guys. Unfortunately, I do not actually know how long I've been recording for because my Microsoft Teams has glitched on me. So we're just going to keep going, and I want to cover just a couple more topics here. The next thing that we're going to talk about is exponents and absolute values, and that's going to do it for today's lesson. So absolute value is very, 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 very straightforward once you learn exactly what it does. Right? So let's go ahead and talk about absolute values before exponents. Okay, so what is an absolute value? Well, absolute value is denoted as if we have any number, right? And we're talking about the absolute value of that number, we draw two bars around it. And that's what an absolute value looks like. And we did have an absolute value on the prelim exam, so now hopefully this might start to make sense for you. So what does an absolute value do? Well, if x is already positive, or technically 0, so if x is greater than or equal to 0, right? That's the same thing as saying if it's 0 or positive, then what it does is absolute value of x just gives you back x. And what's, a good example of this? Well, say I have absolute value of 3. Well, it's just going to return 3. It doesn't do anything to it. It doesn't change it at all, right? However, if I have a negative number, so if x is less than 0, then the absolute value of x is going to flip the sign. I know this might seem counterintuitive, me writing a negative number here, but what's really happening? So again, let's do a quick example. Say x is -3, right? Okay, so what's really going to happen here? Well, it's going to flip the sign. It's going to be -3. And what do we know about two negatives? Well, it cancels both of them out, right? And we are just left with 3 again. So the easier way to consider this is if you have a positive number or 0, it's going to remain positive or 0. If you have a negative number, it's going to make it positive. And that's it. That's all an absolute value does. Okay? So I'm going to erase this, and we're going to look at a couple properties here, all of which should, in theory, make sense. So again, if I have any number in an absolute value, this is going to be equivalent to that negative number in an absolute value. Why? Because again, what's going to happen? Well, that just comes out to be a, right? And doesn't really matter if this is negative or if it's positive, because absolute value is going to make it positive anyway. And we get a is equal to a, right? So again, just keep in mind all the absolute value is doing is making any number positive if it wasn't already. And if it's 0, then it remains 0. As far as multiplication inside of an absolute value is concerned, so if we have a times b inside of an absolute value, well, we can break this up and we can say, well, it's the absolute value of a times the absolute value of b. And you don't feel necessary or don't feel like you have to write parentheses like this. It's totally not necessary. When you have two absolute values next to each other, it's implied that that they're being multiplied. So this, again, it's implied that it's the absolute value of a times the absolute value of b. Okay, so you don't need to write any parentheses or the dot for multiplication. Okay, next up we have as long as b is not 0. So as long as b is not 0, we have the following. So I'll write an if. We have the absolute value of a fraction. So the absolute value of a over b is still going to be the same thing as if we broke it up to the absolute value of a over the absolute value of b. And again, the reason that b can't be 0 is because then the fraction, the world, the computer, it all blows up, right? You can't have divided by 0 in a fraction. So b can't be 0, but otherwise this is going to be very similar to multiplication, right? If you have division going on inside of an absolute value, you can split it up. If you have multiplication going on inside of an absolute value, you can split it up. Okay. Next up, we are going to have kind of a slightly confusing one at first glance. So we have a minus b inside of an absolute value. And believe it or not, this is still going to be equivalent to b minus a inside of an absolute value. So for this one, I do want to do a quick demonstration. So if you have absolute value of, let's say, 5 minus 3, well, we know that this is going to be absolute value of 2, right? So absolute value of 2. And if we have the absolute value of a positive number, it stays positive, which means it's just 2, right? Now let's go ahead and flip it. So we have, A was 3, right? So we have 3 minus 5. We get the absolute value of negative 2. And remember, if it's negative, it just turns it positive, right? So if it's negative 2 in the absolute value, we just get 2 back. And you see that we get the same number either way, right? So what this is essentially saying is that subtraction can be, like, you can change the order of subtraction. You can change the places of the variables as long as it's inside of an absolute values. Okay? And we'll look at some more things regarding absolute value in just a second here. Now, last but not least, there is one last property which has a super fancy name. It's called the triangle inequality. Okay, and what it states is you have the absolute value of A plus B, and this is always going to be either less than or equal to the addition of the absolute values of them separately. I'm not going to go into a proof. I'm not going to go into an example. I'm only putting this here simply because you may see this in future math classes. For the purpose of our class, we are basically never going to use this. Okay, so see it, recognize it, triangle inequality, that's its name, and I will write it again. Triangle inequality. The first time that you're probably going to see this, if you do go all the way up through the math courses, you're probably not going to see this until you get to calculus. But again, I'm putting it here just so you have seen it, because it is technically a property of absolute values. Okay, so again, let's go ahead and I'm just going to let you guys do this one on your own. Let's go ahead and let x equal negative 8. What I want you guys to do is find the following. I want you guys to find the absolute value of x. I want you to find the absolute value of negative x. And finally, I want you to find the negative absolute value of x. Okay, so give yourself a couple seconds. Go ahead and jump through those. You can even probably do these mentally if you want, and unpause the video when you're ready. Okay, hopefully all of you guys got it. So first one, absolute value of x. Well, we know x is negative 8, right? We just plug in directly. So we get, so I'm just going to write this over here, absolute value of x is equal to absolute value of negative 8. And remember, whenever we have a negative inside of an absolute value, just makes it positive. So we just get 8. Okay, next up we have absolute value of negative x. Okay, well, you can actually approach this in two different ways, and well, let me take that back. You can only approach this in one way, but it might be helpful to think about it in another way. But for the purpose of this, again, we're just going to plug in, right? So if we have a negative already in there, right? Again, it's negative x. So negative 8 inside of an absolute value. And what happens with negatives? They cancel out. We're just left with absolute value of 8. And with the absolute value of 8, nothing's going to happen to it, right? It's already positive. It's just going to stay positive. So absolute value of 8 is just 8. And last but not least, we have the negative absolute value of x. Okay, keep in mind, guys, the negative is on the outside of the absolute value, which means that it shouldn't be affected by the absolute value, right? So we're going to carry that negative through. We have the negative on the outside, absolute value of negative 8, right? And now inside the absolute value, well, we already talked about before, negative 8 becomes just 8, right? But the problem is that there is already a negative on the outside, which means that it retains negativity. It is still negative 8, right? Because this negative here carried all the way through. This negative in green canceled. So this one here that I'm putting a dot underneath, that canceled with the absolute value. That's what the absolute value did. It made it a positive 8, but there was still one negative left over on the outside, and hence we end up with a negative 8. Okay, so hopefully that gives you a decent idea of how we do this with absolute values. Again, if you have any questions, try your hand at the homework, and give me a question or give me an email if things don't make sense. Okay, so that's absolute values in a nutshell. And last but not least for today, I want to talk about exponents. So exponents, give me 1 second to pull my own notes up. Okay, so what is an exponent? We denote exponents by putting a little number up to the top right corner of some other number, namely a variable or an integer or whatever. So an exponent is what I'm circling in green here. That's your exponent, the n. Okay. Now, what does it actually mean? Essentially, what it means is it's telling you to multiply the base. So more terminology here. The base is going to be what I'm underlining in blue. It's telling you to underline, or it's telling you to multiply the base by itself n many times. So let's take, for example, 2 to the third. And I know that we are actually already kind of started exponents when we talked in our last meeting, but for anybody who wasn't there or for anybody who still needs a refresher, this will be good for you. So 2 to the third. What does this mean? Well, it says that we want to take our base, which is 2, and multiply against itself 3 times. So this is equal to 2 times 2 times 2, and 2 times 2 is 4 times 2, which is equal to 8. Again, I promise that's an 8. Okay. So hopefully that makes sense. So let's go ahead and consider what happens when you have variables where you don't have a particular number. So for example, let's say we have 5xy squared. What are we doing here? Well, keep in mind here, the exponent is on the outside of the parentheses. And what that means is we have to apply the exponent to each piece, everything that is inside. Okay, so what this really becomes is, okay, well, we now have 5 squared times x squared times y squared, right? And now, do we know anything about x or y? Do we know what they're equal to? No, right? So they are just the way they are. They are exactly just x squared and y squared. We can't do anything with it, right? But 5 squared, we do know, right? 5 is a number that we're familiar with, and this implies, 5 squared implies that it's 5 multiplied against itself twice, so just 5 times 5, and 5 times 5 is 25. So we finally end up with 25x squared y squared. And that's it. Okay. Now this is going to be different than if I had, let's say, 5 times xy squared, right? Parentheses make all the difference here because now the distribution of the exponent is only going to the things inside these parentheses and it's not going to go to the 5, which means 5 remains the same and we get x squared y squared. Okay, hopefully that makes sense with how exponents interact with parentheses and kind of, again, a brief introduction / refresher for what exponents really do. Oof. Okay, so properties of exponents. Again, I'm going to talk through most of these. I'm not going to give you too many examples, but just for the sake of it, let's go through the properties. So just assume that a is a real number and assume that it's a non-zero number. Okay, so it's any number that's real and not equal to 0. So our first property is any number, doesn't matter what number it is, any number to the 0 power is always going to equal 1. Again, there is technically a proof for this. I'm not going to show proofs in this class like 99% of the time. If you're curious as far as why this is the case, email me on the side or talk to me on the side, and I'll be more than happy to actually explain this in detail. But this is just one of those things that I'm totally okay with you guys memorizing without actually knowing why. Just understand that any number to the 0 power is always equal to 1. Okay? The next property that we have is going to be any number to a negative exponent. Okay, so any number to a negative exponent. What we do here, and this was on your prelim exam, I believe there was a 5 to a -2. So we'll use that as an example shortly. So what we're gonna do here is this essentially implies that you are going to have a fraction. Okay, so when you see right here a negative in the exponent, that means that you're going to have a fraction. And the top of the fraction, so the numerator, is, unless altered by other operations or numbers, it's always going to be 1. So in this case, right, it's nothing else is happening to a to the negative n. So the numerator is going to be equal to 1. The denominator is going to be a to the positive n. So what are we doing? We're saying that the negative turns into a fraction, the negative exponent makes it a fraction, and then you just follow the same normal rules of exponents, but just in the denominator. Okay, so again, on your prelim exam, we had 5 to the negative 2, right? So the negative implies we're going to have a fraction, so 1 over. And now what we do is we just keep the base the same. It's 5. We keep the exponent. We just switch the sign of it. So now it's 5 squared. And we know, again, 5 squared means 5 times 5. So we just get 1 over 25. And this was the example that I was referencing earlier where I said, feel free to just leave it as 1 over 25. You don't have to write 0.04. I'm actually preferring fractions. Okay, so leave it as such. Okay, so again, just a property that you should memorize. It will be used fairly heavily in this course, so make sure that you guys remember what happens when you have a negative exponent. Okay, when you have a fraction to an exponent, all you're doing is you are basically just distributing that exponent to both the numerator and the denominator. So it's the same thing as a to the n over b to the n. Again, just get in the habit of thinking when you see parentheses, it's the exponent is applying to everything that's in the parentheses, right? So in this case, it's applying to the numerator and also to the denominator. Okay, and interestingly enough, as we already discussed, what happens with a negative exponent, right? It turns it into a fraction. Well, if we already have a fraction, so a over b, and this time it's to a, oh, where's it going? Oh no, I lost my screen there. It's to a negative exponent now, so to the negative n. What we do is, again, we're going to distribute, but we have to flip the fraction. So now it becomes b, and we distribute the exponent over a, also to the n. Okay, so all you're doing is when you see a negative sign, if it's just a regular number, I'm sorry, when you see a negative sign for the exponent, if it's, of the base is a regular number, you're making it a fraction. You're making it 1 over that base to the exponent. If it's already a fraction, in the form of a over b, then you're going to just flip it. So it's just going to be b over a. And again, you distribute the exponent. Okay. That one we won't use too much, but still helpful to remember. And the last couple ones are ones that we will use all the time. So the last 3, I heavily advise that you remember, put it on a note card or flashcard for you guys to, really like hammer into your brains. So it's the following. So if we have the same base, but 2 different exponents, and they are being multiplied. So it's a to the n times a to the m. So again, the base here is a, right? And the exponents are different. What we do is this is equivalent to we keep the base the same and we add the exponents. So this is going to be equal to a to the n plus m. Okay? So I'll give let me just go through the rest of the properties and then we'll go through a couple examples as far as how this is actually going to work out. Okay. The next property that you should be aware of, kind of in the same vein. So this was multiplication of bases with different exponents. Now we're going to talk about division of the same base, but with different exponents. So if we have a to the n over a to the m, well, intuition, if the result of the multiplication was that we're adding, the result of the division, you might assume, is going to be subtraction, and you'd be correct. We're going to keep the base the same, and now we just get n minus m. And you know that it's n minus m because, again, we're doing the numerator exponent first, okay? So the n will always be first, and then subtracting the exponent from the denominator. Okay, so I'm going to erase both of those. Hopefully you guys got that down. And the last thing that you should be aware of is, okay, well, that's what happens if we have, the base is the same and the operation is multiplication or division. Now what do we do if we have one base, so a to the n, and this is all to the power, it's all being raised to another exponent. So we have the base is a, it's being raised to the nth power, and now it's being raised again to the mth power. Sounds very weird, mth. So what we do here is this is going to be equivalent to a to the n times m. Okay, and that's it. You just multiply the exponents. Okay, so what I want to do here is I want to make sure that you guys understand this. Let's just go through a couple very quick examples and we will call it a wrap for this lecture. Okay, so let's see if you guys understand the same general idea. If we have 7 to the negative 1 times 7 to the third power, what are we going to do here? And again, that is a 3. Okay, so 7 to the third power. So if you guys want to just pause, give yourself a quick second, check the properties that we just talked about. What are we doing? It's the same base, and then they're being multiplied, but the exponents are different. Well, the idea here is that we're just going to take 7, right? The base stays the same. And what we do, because they're being multiplied, is we add the exponents. So negative 1 plus 3. This is the same thing as 7 squared. And that is 7 times 7, which is 49. Okay. Let's go ahead and do one more. Okay. So the last one that I want to do here is I want you guys to simplify this. So if you have 5 to the 10th over 5 to the 12th, what are you going to do? Again, give yourself a couple seconds, pause the video if needed, and then we'll go through it. Okay, hopefully you guys got it. So again, the idea is when you have the same base, different exponents, and there's division, we are going to keep the base the same, but we are going to subtract the exponents, right? So it's 10 minus 12. And 10 minus 12 gives you negative 2 in the exponent. Now we're not done. We haven't actually simplified this. We still have an exponent, right? We don't technically have a completed answer yet. So 5 to the negative 2, you would have basically gotten half credit if you stopped here. We have to keep going and drill down, make sure that we get rid of all the exponents. So, well, 5 to the negative 2, this should look familiar, right? We had this before. What do we do when we have a negative sign in the exponent? Well, that's going to be equivalent to 1 over 5, and then we flip the sign of the exponent, right? So negative exponent implies the fraction, so we have 1 over 5 squared, and that's going to be the same thing as 1/25. And that's it. All right, guys, so give your homework a shot. I'm going to be posting this like as soon as possible, yeah, let me know if you guys have any trouble, and I will talk to you all on Monday. Enjoy the remainder of your Sunday, guys. Have a good one.